Good morning, professors. We are Team 60057 and our research topic is isoaerial and isoperimetric deformation of curves. At the beginning, we were inspired by a slug when it tried to decrease its surface area to avoid being vaporized. Because of this phenomenon, we successfully figured out our research direction, a curve reducing its parameter in the fastest rate. Inspired by the slug, we related this idea to two classical mathematical problems, isoperimetric inequality and brachysterechrome curve. Isoperimetric inequalities states that circle has the maximum area among all the shapes with the same parameter. That is equivalent to circle having the minimum parameter among all the shapes with the same area. Brachysterechrome curve investigates the path of a particle to slide down in the shortest time. Our research topic can be said to be the sum of these two problems. How to deform a smooth curve such that its parameter will decrease in the fastest rate subject to fixed area. We started our project by studying isosceles triangle because it was simpler for studying. We wanted to minimize the rate of change of parameter with the area of the triangle fixed. We tackled the problem by separating it into two cases. First, vertex A moves upwards. Second, it moves downwards. We assume the speed of the three vertices is constant. By setting the range of change of area to be 0, we find that vertex A could move either upwards or downwards for isosceles triangle. The equations of how the vertices move are shown on the screen. To minimize the range of change of parameter, vertex A should move downwards for thinner triangle, and it does the opposite for flatter triangle. The corresponding angle can be calculated by these equations. After finding out how the vertices move, we studied the locus of the bottom two vertices. We set up this differential equation and we find this equation of the path after solving it. Here is an example. The triangle will deform along this path until it becomes an equilateral triangle. After trying isosceles triangle, we entered the core part of our project, the problem of smooth closed curve. Here, the blue line is the initial curve and the red line is the curve after time t. With fixed area, we would like to find a function v to minimize the instantaneous rate of change of the parameter. Obviously, it can be tackled by calculus of variation, so we learned to use Euler-Lagrange equation to solve it. However, only constant area is not enough for us to define the velocity function well. We had to introduce the conservation of total kinetic energy of the curve as another constraint. Also, the velocity u along the normal direction should be used instead of v along the radial direction. The definition of v and u are illustrated by the figure here. As the kinetic energy of the string was constant, we got these energy constraints. By setting up the functional j and solving it by Euler-Lagrange equation, we successfully find the function v, lambda, and lambda prime, such that it optimizes the rate of change of the parameter with the area still fixed. Here is an example which shows the function v for an ellipse. However, it was quite difficult to check whether the result we obtained was a maximum or minimal by ordinary methods like the Jacobi condition and Legendre condition. So we learned to use inner products, as it would be less complicated to check for maximum or minimum. Here are the expressions of the range of change of parameter and the constraints. We define A dot B, R1 and R2 as shown such that our functional and constraints could be transformed to inner product form. We minimize v dot r1 subject to v dot r2 and v dot v to be constants. And this figure showing the vector r1, r2, and v. By choosing the negative projection of r1, we find lambda, v, and lambda prime. As shown on the screen, they are actually the same as what we find in the previous part. Since function v solved by inner product method minimized v dot r1, we can conclude that the instantaneous rate of change of parameter is minimized. Although we got these expressions, it was too complicated for us to deduce the deformation easily. From geometrical view, the deformation should be coordinates-free because no matter where the curve is, it changes in the same manner. Therefore, we learned to describe it by some coordinates-free quantities like curvature and length. Then we got these results. Surprisingly, the function u is the standard score of the negative curvature. That's really out of our expectation. And we can use these expressions to describe how the curve changes easily. It can be illustrated by the figure here. If part of the curve has a larger curvature than the average curvature, it will move inwards, and otherwise it does the opposite. What's more, we can deduce from these expressions, gracefully, our results fulfill the isoparametric inequality. During the deformation process, the parameter of the curve is decreasing until it reaches an intermediate state, which the parameter will be the smallest. U equals 0 when the curve reaches the intermediate state. At the same time, curvature equals a constant, which implies that the curve becomes a circle, echoing the isoparametric inequality. We also studied the dual problem, isoparametric deformation, as it was quite natural to think of it. They have the same meaning to a certain extent. They both study the shortest time to deform. And the results are shown on the screen. To conclude, we solved the problem for isosceles triangle completely. We also solved the problem for closed curve by both analytical method and geometric method. Lastly, we could use some geometric quantities to describe the change of curves. The table shows some important results we got in the project. In fact, we could further study our problem in 3 ways. First, the movement of the center of mass of the curve. Second, the rate of change of the curvature. Third, the time taken for the curve to deform to a circle. For the rate of change of the curvature, we find that it is such a function. Maybe it helps us find the time taken. And for the rate of change of area, it is like this, which involves an integral of square curvature. This term is quite special as we cannot easily express this by other variables. Therefore, if we want to find the time, we should be able to control the rate of change of the following quantities. We hope we could solve the problem if we have time in the future and someone interested in this topic could try to solve the problem. Thank you.